Hello guys, today we're going to be doing further mathematics, probability statistics, paper 4-3 of the May-June series of 2021. So let's get started. So for the first question, it's an inferential statistics based question where farmer A grows apples of a certain variety. Each tree produces 14.8 kgs of apples on average per year. Farmer B grows apples of the same variety and claims that his apple trees produce a higher mass of apples per year than farmer A's. So what he's trying to say is that the mean of farmer B's is going to be greater than the mean, which is 14.8 of farmer A. The masses of apples from farmer B's may be assumed to be normally distributed. Fine. A random sample of 10 trees from farmer B is chosen. The mass x kg of each of apples produced in the year are summarized as follows. Test at the 5% significance level where the farmer B's claim is justified. Right. So for this, basically we start off with our hypothesis whenever we do testing, right? And farmer B is claiming that his apple trees produce a higher mass of apples per year than farmer A's, meaning to say that on average the mass of his is greater than the mass of farmer A's trees. So H null, our null hypothesis, always states that the mean will be equal. So that means mean of farmer B equals to farmer A, in this case 14.8. However, our alternative hypothesis is what farmer B is claiming, which states his mean of apples is greater than 14.8. Alright, moving on. Whenever we have testing, we need to get the S2 value, which is the unbiased estimate. So before that, let's just note in some values where the sample size n equals to 10 and the sample mean is equal to 15.2. Why I say 15.2 is because it's just going to be the sum of x divided by number of terms. Okay, now that we have the basic data, we can plug it into our formula. So we need S2. Okay, and S2 is equal to 1 divided by number of terms minus 1, multiplied this with sum of x squared minus sum of x the whole squared divided by number of terms. This produces the unbiased estimate value. So now let's plug in the values we have. Is equal to 1 by n minus 1 is 1 by 9. Bracket this with sum x squared being 2313 minus 152 the whole square divided by 10. Right, so we need to plug this into our calculator. Okay, so we have 1 by 9 multiplied by bracket 2313 minus 152 squared by 10, and we get here 13 by 45. This is what we're going to be using in calculations, but Cambridge expects us to get the integer, the decimal value as well. So we have here 0.28 recurring. So right, you can keep it to a few significant figures. 0.288. Now let's keep it to 4 decimal places. Alright, now that we've got that S2, now we have to do the testing. To find the test statistic, there is a formula for that as well, which is T is equal to x mean minus mu, which is the stated mean, whole divided by the root of S2 by n. And now that we've calculated S2, we have all the values that we need to proceed with this calculation. So sample mean x is 152.2, sorry, 115.2, minus this with mu, which is 14.8, we'll divide this with okay, the root of 0.2889 We'll divide this with the number of terms 10. Okay, so this is our test statistic. Let's calculate this. So I've saved my previous answer as in the calculator itself, so now that I won't have to calculate the value again. So root of answer by 10, and this is equal to 2.353. 2.353. Remember, we're always supposed to take it in 4 significant figures because every critical value in the distribution tables are in 4 significant figures. Now we need to refer to our t distribution. So let's go over here. Yeah, t distribution. We can either use t values or the z values here. We use t values because the sample size is only 10, and 10 minus 1, which is the degrees of freedom. Right, so let's just write the degrees of freedom first. Degree of freedom equals to 10 minus 1, which is n minus 1, which equals to 9. As you can see in the t distribution table, there is a degree of freedom 9 column right here, row right here. So we don't need to refer to these values here. So since we're using t distribution, our test statistic is written in t. Okay, moving on. The other value that we need to calculate the critical value is our p value. So to calculate p value, first we have to realize if this is a single tail test or if it's two-tailed. In this case it's single tailed because mu is greater than 14.8 in the alternative hypothesis, and we're testing this at a 5% significance level. So a single tail test, p is equal to 1 minus alpha. This is for one tail, and so in this case is 1 minus alpha, where alpha is 5%. So 1 minus 0.05 gives 0.95. Hence, when we refer to a critical value from the t distribution, we put degrees of freedom, comma, probability, which is equal to, now we have critical value 1.833. So this is our critical value, and in every testing based question you always have to compare the test statistic and the critical value. So our test statistic 2.353, comparing it with 1.833, you can see that our test statistic is quite large compared to our critical value. So let's put this operator here, and since the test statistic is greater than the critical value in a t distribution test, we have to reject h naught. Reject the null hypothesis. Right, so now that we reject it, we have to frame our conclusion in a sentence structure as below. So when we reject h naught, we have to say there is sufficient evidence to suggest or to accept. Now we have to write the alternative hypothesis, which is just farmer B's claim. Yeah, that's our conclusion. Right, moving on, we have Wilcoxon match pair sign rank test. So let's see the question here. It says the random selection of 9 flavors of chocolate are being judged by two taste testers, which give marks out of 100 for each flavor of chocolate, and there are totally 9 samples, 9 flavors with 2 taste testers. Carry out a Wilcoxon match pair sign rank test at 10% significance level to investigate whether on average there is a difference between marks awarded by the 2 taste testers. Right. Okay, so for this we have to obviously state the hypothesis first, and to state the hypothesis, just put h null, and it says that we have to test whether there is a difference awarded by the 2 tasters. So difference between marks. Okay, so initially the population medians, we always talk about population medians when it comes to Wilcoxon match pair rank test. So m1 is equal to m2, right? And h1, the alternative hypothesis, says that the population medians are not equal. Remember, mean is used by inferential stats and population medians is used by non-parametric tests. So this is a non-parametric test, Wilcoxon match pair. So uh, we have to use a non-parametric formula, which is going to be relating with population medians. Okay, now we need to find the differences because this is a match pairs sign rank test. Whenever we have match pairs, we have to subtract the top value with the bottom value for each and every single one of them. So let's write here. Let's start. 72 minus 84 is negative 12. Moving on, we have 86 minus 72, which is positive 14. Next we have 75 minus 74, which is positive 1. 92 minus 95, which is negative 3. 98 minus 85, which is negative 13. No, wait, that's positive 13. Moving on, we have 79 minus 87, which is negative 8. We have here 87 minus 82, which is positive 5. 60 minus 75, negative 15. And finally, 62 minus 68, which is negative 6. Okay, so moving on, we have our differences. Okay, now we have to rank them according to the values. We do not consider the sign values for the rank. So do not consider the sign values. So the lowest obviously is going to be 1. The second lowest is going to be the 3 here. Remember, we don't consider negative 3, we consider just 3. Third one would be the 5. Fourth is the 6th. 6 right here. 5 should be this one. Next we will have negative 12. So 6 here. 7, 8, 9. So that's our ranks. Now we need to find the signed rank. Signed rank. Okay, how do we find signed rank? Based on our differences. The symbol on our differences is going to be our signed rank. So our signed rank over here is going to be 6. And whether it's positive or negative will be decided by the differences. The difference over here is negative. So that means we will have a negative 6 as our rank. Next we have here a positive 8 rank. And our difference is also positive, so our rank remains positive. 1 is our rank here, and that's also a positive difference, so we have 1 as a rank. 2 is our rank over here, but it's a negative difference, so our rank becomes negative 2. Now our rank is 7, so let's put 7 here. It's a positive difference, so it's going to be a positive rank. Next we have here 5, which is the rank, and this is a negative difference, so negative 5. This is 3 with a positive value, so it's just going to be 3. 9, but this is a negative difference, so you have negative 9. And then 4 with a negative difference, negative 4. Okay, just seeing about the values, right? Yeah, sure, it's right. Okay, now moving on, we need to calculate something called P and Q. P is equal to the sum of all positive ranks, which is 8 plus 1 plus 7 plus 3. 8 plus 1 plus 7 plus 3 equals to 19. And now we need to find Q. Q is equal to the sum of all negative ranks. Okay, but we look at the absolute value. So 6 plus 2 plus 5 plus 9 plus 4, which is 7, 8, 13, 26. And just to ensure that our ranks are correct, we can just use the formula of summations, which is number of samples multiplied by number of samples plus 1 whole divided by 2. This means that our P and Q should sum up to 45, in which case it does. Now to calculate the test statistic, okay, we have a formula. T is equal to the minimum of P comma Q. What does this min mean? It means that the smaller value between P and Q. In this case it's 19, so we have here 19. What I mean to explain by this is T equals to min of PQ. P is 19, Q is 26. So which one is smaller, 19 or 26? It's 19. So test statistic is 19. Moving on, we need to find a few other values to get the test statistic. So for a Wilcoxon signed rank test or any kind of test, we use this. So what are the things we need to find? First thing we need to find is the sample size. Next thing we need to find is the level of significance and whether if it's one-tailed or two-tailed. So let's first find the sample size. N equals to, and we have here 9 flavors here. 9 flavors. So we've narrowed it down to this row. N equals 9. Now, whether it's one-tailed or two-tailed, let's see. It says it's a 10% significance. Okay, so that means that we have to look over here. Okay, it's going to be 0.1 over here, and that means it's going to be two-tailed. But just to ensure that this is a two-tailed test, you can see that it's just not equal to. It doesn't say that M1 is greater than M2. It doesn't say that M2 is greater than M1. It says M1 is just not equal to M2. So that means M1 can take a value below or above M2, which means this is a two-tailed test. We're looking at values higher and lower than M2. So at a two-tailed test, 10% significance level, we have here and here. So that means a critical value will overlap over here, 8. So that means we should write critical value from tabular column is 8. Okay. Moving on, we have to compare the test statistic and the critical value, which is the final step of every single testing. So we have here 19 and we have here 8. And a Wilcoxon match pair sign rank test, we have the test statistic greater than critical value. In this case, we accept H null because in a non-parametric test or any non-parametric test, when the test statistic is greater than the critical value, we accept H null. But for chi-square test and inferential, we reject. And so we have here there is insufficient evidence to suggest that. Now we write our alternative hypothesis, which states that there's a difference between marks. So that means state that the marks differ. That's our conclusion. Okay, moving on, we have another inferential statistics based question, and this is a two sample test, so this is going to be a bit more harder. So we have here a random sample of 50 from country A, which represents with X. So that means the number of samples for X equals to 50. These are some things that we need to note down before we even start. So 40 adult males from country B represented with Y. That means number of samples of Y is equal to 40. And the 95% confidence interval for the difference between the mean heights of country A and country B. Okay, very simple question. Let's solve this. So for a confidence interval CI, formula for this, which is equal to difference of the means, which is X mean minus Y mean, plus or minus. Now we use a Z or T value which is multiplied by the root of S2. So do we use Z root S2 or do we use T root S2? Since our sample sizes are 50 and 40, our degrees of freedom, which in this case would be 90, which is the sum of 50 and 40, minus 2, which is 88. Looking at the T distribution test, there is no degree of freedom of 88 which they give a corresponding value for. Hence, we are not using a T value, which means we are going to use the Z value. So Z times root of S2. So what are the values that we already have? Well, we have none of these. So let's calculate some values and then we'll plug it in. So what is mean X? Sample mean of X, which is equal to sum of X divided by 50, which is the sample size. So 89 by 50 is equal to 1.78. Now we need to find the sample mean of Y, which is equal to 67.2 divided by 40. This is equal to 1.68. Right. Finally, we can calculate the Z value. Okay. So how do we find the Z value? So when you go to the table here, this is where the Z values lie. you can see that the only thing we need to know is the p-value. Then we can calculate z-value. So what is going to be the p-value? So it says over here 95%. 95% is 0.95 in decimal, right? So from 0.95 to 1, we need to find the midpoint. Okay, so this is one entire line. What's the midpoint between 1 and 0.95? Which is going to be right here, which is going to be 0.975. This right here is our p-value. That means our critical value will be 1.960. Okay, so that means z is equal to 1.960. So we already have a lot of pieces of information now. Into our formula, all we need is S2, which is going to take some time to calculate. But before we plug in these values, let's calculate S2. So to find S2 in a two-sample test, is going to be to find the S2 of x, S2 of y, and use either the pooled estimate or the unbiased estimate formula. So let's first find S2 of x. Actually, I will use this in public. To find S2 of x, it's going to be, as the formula I stated in the first question, 1 divided by number of terms, which is 50 minus 1, so 1 by 49. Multiply this with sum of x squared, 159.4, minus this with 89 squared, divide this with number of samples, 50. Alright, which is equal to, now let's plug this into our calculator. 1 by 49, multiply this with 159.4 minus. Okay, so when I plugged in the values in the calculator, I'm getting a proper 1 by 50, which is quite convenient actually, so that our values become a bit more accurate in calculation. 1 by 50, which is equal to 0.02, if I'm not wrong. Yeah, it's 0.02. Okay, moving on, let's find S2 of y. Let's use that with this. S2y is equal to number of samples minus 1 by number of samples minus 1, so 1 by 39. Multiply this with sum y squared, which is 113.1, minus this with sum y squared, which is 67.2, square this with and divide with 40, which is the sample size. Okay, so now that we've done that, we get a value of, well, let's put this in the calculator. 1 by 39 multiplied by 113.1 minus 67.2 squared by 40. We get 17 by 3250. This is not going to be a clean decimal value. This is going to be quite a long value. So let's take this into our calculations. This is equal to 0.00523. Fine. 30. Let's take it to 8. Okay, let's keep it a bit specific, but we're going to be using this value right here in our calculations. Okay, now do we use pooled estimate or combined unbiased estimate? So for pooled estimate, there's only one condition that we need, and that is that the population variances of the two samples of x and y must be the same. Nowhere does it specify that the population variances are the same, so we use the formula for S2. Now to find the formula, it's very simple as well. S2 is equal to S2 of x multiplied by degree of freedom of x plus S2 of y multiplied by the degree of freedom of y. So what we're basically doing is that we're just reversing the step. We don't need this 1 by 49 or 1 by 39. We just put this over here and this over here, and we divide this with the degrees of freedom combined. So nx, number of terms of x, plus number of terms of y minus 2. So using this formula, we can just plug in our values. Okay, So we have here s2 of x, which is 0.02, multiplied by degrees of freedom of x, or n minus 1, which is just 49. Wait, this is the pooled variance formula. This is the pooled variance formula. We don't need this formula. So for the unbiased estimate formula, all we need is all we need is s2x by number of terms of x plus s2y divided by number of terms of y. Got a bit mixed up there. So using this we can get 0.02 divided by number of terms of x, which is 50, plus 17 by 3250, and we're just multiplying the denominator for this one, divided by 40, so times 40, which is equal to 69 by 130,000. Let's put this in black. So 69 by 130,000. So now to calculate the confidence interval, CI is equal to, we've got lots of space. Okay, yeah. CI is equal to mean y minus mean x minus mean y, which is 1.78 minus 1.68, which is just 0.1. So 0.1 plus or minus the z value. So plus or minus z value of 1.960. Just put 1.96 root of this s2 value. I'm just going to represent it with s2, and we can calculate this right hand side first. So 0.1 plus or minus root of this value multiplied by z, which is 1.96, is equal to 0.0451553. So like we put it to 0.45155. Okay, so when you do 0.1 plus or minus, so which operation do we do first to find the confidence interval of value? So we need to first do the minus operation, and when you do the minus operation first, we get our first the first value of our interval, which is 0.1 minus this, which is 0.0548. Three significant figures, 0.054 of 8, comma, and to get this value back we can just do this. Okay, and then now we add that with 0.1 plus 0.45155, which is equal to 0.145. So let's put this here, and there you go. That's our answer right there. That's the confidence interval for the two sample test. Fine. Right, now we have probability generating functions. Find ex and variance of x when this random variable x, which is a discrete random variable, takes values 0, 2, 4, and so on. So it multiplies by 2. No, adds by 2. Okay. The probability generating function of x is given by gxt is 1 by 3 minus 2t squared. Find ex, find variance of x. Fine. So to find e of x, you have to know that gx differentiate, and you plug in t equals 1 is equal to e of x. This is something that you must know before attempting the question. So moving on, let's get the ex value first, and that will be represented in red. Okay, to get ex, first we need to differentiate gx of t. Gx dash t is equal to, now there is a formula for this, which is ux u dash x multiplied by vx plus minus u of x multiplied by v dash x whole divided by v of x whole squared. This is how you differentiate a fraction. We could use the normal laws of differentiation, but this is just a possibility on how to do it. So we have here when our numerator is u of x and our denominator is v of x. So when you plug in this formula, you get u dash of x, which is the differentiate of 1, which is 0. Multiply this with v of x, which is 3 minus 2t squared, minus this with 1, multiply this with, let's put this in brackets, multiply this with the differentiate of 3 minus 2t squared, which is negative 4t squared, no, negative 4t. We whole divide this with 3 minus 2t squared, a whole squared. So we don't need to simplify that. T squared whole squared, which is equal to, now this becomes 0, this becomes negative 1 times negative 4t, which is just positive 4t. Divide this with, and we don't need to simplify this, so it's alright, 2t squared whole squared. Fine. Now, as I said, gx differentiate and you put in t equals 1. So when t equals 1, our value of ex becomes 4. It's going to be 4 multiplied by 1. Divide this with 3 minus 2 times 1 squared, whole bracket, square this value, which is equal to 1. Well, it's equal to 4. The denominator is equal to 1. So it's equal to 4 by 1, which is 4. So this is our e of x value. Let's just put that in a nice box. E of x is equal to 4. Yeah. Okay, moving on, we need to find the variance of x. This I'm going to represent it purple. So to find the variance of x, there is a formula for this as well, which is equal to the gx of t, gx double differentiate when t equals 1, plus gx dash 1, which is just e of x, minus this with open bracket gx dash 1. Once again, this is just e of x and whole square this. That's the formula to find variance. So how do we find this? Well, let's first find gx double differentiate. So gx double differentiation of t. So how do we do this? Let's get our, so this is our differentiated formula, which is this right here. So now we have to use, let's just rearrange this equation first. Okay, so instead of writing it like that, let's just rearrange this to 4t, multiply this with 3 minus 2t squared by negative 2. Remember, this is going to be negative 2 because it's a fraction. Okay, now how do we differentiate when we have, well, how do we differentiate with respect to t when we have over here two different products? We have to use the product rule, which is ux multiplied by, multiply this with, okay, let's write this in green to give it as a formula. So differentiate will be ux times v dash x plus u dash x times vx times v of x. Okay, so this is the product rule. You can do it either ways. You can differentiate u first and then get times it with v and then do this. Since it's plus, either way doesn't matter. So let's just use this now. So u of x is going to be 4t. V of x is going to be 3 minus 2t squared whole bracket negative 2. So let's first differentiate this. Let's do it in this pattern here. U of x, which is 4t, we multiply this with the differentiate of v dash x, which is just differentiation of this, which is equal to negative 2. We have to multiply our exponents. Then when we differentiate inside, we get negative 4t. So multiply this with negative 4t. And then we just write our exponent over here with negative 1 also. So negative 2 minus 1. It's going to be 3 minus 2t to the power of negative 3. Okay, so this is going to be our result for the first one, and then we add this with the result of the second one, which is just going to be u dash of x. So that means differentiate of ux is 4, and we multiply this with v of x, which is just this value here. So let's we can write that very simple. So 3 minus 2t squared whole divided by negative 2. Okay, so there's no need to simplify. I mean, if you want to, you could, but remember, we are not trying to find that double differentiate right now. Okay, so just to give you a hint, the double differentiate, this is just okay. So we are not just trying to find the double differentiate, we are trying to find when t equals 1. So instead of finding the entire thing, we can just plug in t equals to 1. But before that, we can simplify this a bit. So 4t multiplied by negative 2 times negative 4t is just 16t. It's going to be 16t squared. No, 32t squared, sorry. 32t squared. And then we can just write our equation here, which is 3 minus 2t squared of negative 3 plus 4 times 3 minus 2t squared by negative 2. Okay, now we plug in t equals to 1. So let's plug this in. 32 times 1 squared, multiply this with 3 minus 2 times 1 squared, then whole bracket to the power of negative 3. Okay, and that result is 32, and then we add that with this. So it's 4 multiplied by 3 minus 2 multiplied by 1 squared bracket negative 2, which is going to be 32 plus 4, which is 36. Let's just keep this in a different line then. So that means gx dash dash when t equals to 1 is equal to 32 plus 4, which is equal to 36. Okay, so now that we found this, we can just plug this into the equation over here. So that means variance of x, let's put this in black. So that means variance of x is equal to 36 plus expected value, which is 4, minus expected value squared, which is 4 squared. It's equal to 40 minus 16, which is equal to 24. So that means our variance of x equals to 24. That's how you find the variance. Okay, moving on. Find the probability that the x value equals to 4. Okay, so let's first get our gx of t so that I can just be reminded of what we're doing. Gx of t is equal to, and we got here 1 divided by 3 minus 2t squared. Okay, this requires a little bit of intuitive thinking. So what I'm going to do here is trying to get it into a geometric series, because over here, if you look into the the normal statistics or pure math, let's see where the list of formula for this is. Yeah, so for the sum of a geometric series, sum to infinity is a divided by 1 minus r. Okay, where r absolute value is less than 1. So we have, this is the thing right here, and we have a similar structure, except a must be equal to 1. So the first term of this geometric must be 1, because a, which is the first term, must be 1. Okay, but over here we can't have 3, we need to have 1 over here, 1 minus r. So to get this value as 1, we just need to factorize 1 by 3 of this thing, which is equal to 1 by 3. We'll put dot here to indicate multiplication. divided by 1 minus 2 by 3 t squared. Okay, now that we've done that, we factorized out 1 by 3, and now you can see that it looks a lot like our geometric series. 1 divided by 1 minus r, 8 divided by 1 minus r, where a equals 1, so let's put a equals 1, and r is equal to 2 by 3 t squared. Okay, so we have this for now. So we can simplify 1 by 3, multiply this with. So if we simplify, this is the sum to infinity. So our geometric series will have our first term as 1, our second term as 1 times the ratio, which is 2 by 3 t squared, and our third term will become 2 by 3 t squared multiplied by 2 by 3 t squared, which is 4 over 9 t squared, t to power 4, plus, now let's do it again, it's going to be 8 by 27. We're just multiplying the ratio with it, okay? Nothing too complex just yet. And yeah, t to power 6. And this goes on until infinity. Okay, so this is a convergent series because r is absolute value less than 1. Now to find the probability that x is equal to 4, we need to find the coefficient of where t to the power of x, which is 4. So t to power 4 is over here, right? This right here is t to power 4. Now we need to look at the coefficient, which is 4 by 9. But you have to realize we factorize 1 by 3 out of this entire thing. So the coefficient when 4 by 9. Okay, we're going to multiply this with 1 by 3. Okay, because we're taking out our coefficient and then multiplying it with what we factorized out, which is equal to 4 by 27. This right here is the probability that x equals 4. So yeah, fine. Now looks like this is going to be a question on chi-square test. Fine. Explain how the information tends to support the manager's suspicion. Okay, so Chai packs China mugs into cardboard boxes. Chai's manager suspects that the breakages occur at random times and the number of breakages may follow a Poisson distribution. He takes a small sample of observations and finds that the number of breakages in a 1 hour period has a mean of 2.4 and a standard deviation of 1.5. Explain how this information leads to support the manager's suspicion. So first we have to identify what is the manager's suspicion. He suspects that breakages occur at random times and that the number of breakages follow a Poisson distribution. We need to follow this. This is what our main suspicion is. Number of breakages follow a Poisson distribution. So let's just cut that for now. Okay, so how does the information tend to support this? So our expected value, which is just the mean, okay, I'm going to call this mean here, mean equals to 2.4. Let's put in the values we know. A standard deviation, which is represented with this symbol sigma, equals to 1.5. And so what is variance? Variance is just standard deviation squared, which is equal to 1.5 squared, which I think is 2.25. Yeah, it's 2.25. Okay, now there is a thing. So when the mean is almost equal to the variance, okay, that means that it does tend to the Poisson distribution, because the Poisson distribution needs to have the mean near equal to the variance. So we can write for conclusion, the mean is almost equal to the variance, or yeah, almost equal to the variance. So the Poisson no, capital P on distribution may be suitable. Right, we have to have a degree of uncertainty. We cannot say it is suitable. We have to put may be unsuitable, may be suitable, because we don't know if it is. That can be tested with what we have here to test whether the larger sample when we do a goodness of fit test. So let's see. The manager now takes a larger sample, claims that the number of breakages in the 1 hour period may follow a Poisson distribution. We are now testing the claim that we stated above. The numbers of breakages in the random sample of 180 1 hour periods are summarized as follows. Okay. Mean number of breakages calculated from this sample is 2.5. Okay. So that means that in a Poisson distribution, lambda is equal to 2.5. That's just something you have to identify. Okay, so lambda equals 2.5. Fine. Use the data to carry out a goodness of fit test at the 10% significance level to test the claim. Okay, so whenever we do a test, there are a few steps. First step is to find the test statistic. No, the first step is actually to get the hypothesis, which is going to be a null and alternative hypothesis. Second step is going to be a test statistic. Then the third step is going to get the critical value, and finally the fourth step is to compare. And using this comparison, we get the final step, which is the conclusion. So step 1, hypothesis. I will represent this in blue ink. So H null, the null hypothesis should state that the Poisson distribution, okay, the claim is that follow a Poisson distribution, okay, and 2.5 is the thing. Yeah, so that means Poisson distribution is a good fit to the data. Okay, and H null, that's what H null states. Now H1, which is our alternative hypothesis, H1 will just state the direct opposite, which is Poisson distribution is not a good fit to the data. Okay, so this is our hypothesis. Moving on, now we need to find the frequencies, the expected frequencies. So to find that, we have to go back to our list of formulae, where we need to go to the statistics column right here. Yes, over here we can find the Poisson distribution. This formula we need right here. This is what we need. And it states that we need to do E times negative lambda multiplied by lambda to power r divided by r factorial. Quite a complex formula, but it can be just plugged into the calculator. We'll get the values. So yeah, but you have to understand that there's total sample of 180. That means our sample size equals 180, or our total frequency is equal to 180. So that means that we have to calculate for 180, multiply this with e to the power of, it says negative lambda, so negative 2.5, multiply this with 2.5 to power r divided by r factorial. This is the formula. This is the formula to find the expected values of each, expected frequencies of each ER. Okay, so when we have, this is r equals 0, r equals 1, 2, 3, 4, 5, 6, and so on. So let's put here. So for the first one, when r equals to 0, 180, multiply this with e lambda, which is e to power 2.5, negative 2.5, multiply this with 2.5 to power 0. Remember, r is going to be the number of breakages, 0 here, and we do 0 factorial. Remember, 0 factorial is 1, and it gives us a frequency of 14.775. So for the first one, it's going to be 14.775. Okay, moving on. We need to find the next one, which is going to be here. When r equals to 1, when the number of breakages is 1, we have 36.938. 6.938. 8. Okay, moving on. Third one. When number of breakages equals to 2. We just finish off the R values and then just replace it with we just increment it because we don't need to change anything else. 46.173. 73. Okay, when R equals 3 now. So just remember in the formula it's R factorial. So we just replace R or increment R as opposed to say it. And we have 38.477. 477. I tend to keep the 5 significant figures just so that we get the most accurate value of this. Now when R is incremented again, we have 24.048. 8. Next, when R equals to 5. Oh wait, this is not R equals 5. When R equals to 5, we're going to have here 12.024. 024. Now when it's equal to 6, we're going to write it here, or I can still write it here. So when it's equal to 6, we have 6 and 6. 5.01. 0100. Let's put 00. 0101. Sorry, my bad. 01. And when R equals to 7, we have here 1.789. Right. We have here 1.789 when R equals to 7 more. Right. Yeah. Okay, yeah, moving on. So when R equals 1, R equals to 2, R equals to 3, R equals 4, 5, 6, 7. This says 7 or more. So it is this right here. This is what we have, 7 or more. Okay. So first of all, when we have 7 or more, I realize where my mistake is. We cannot calculate when 7 or more because it can take any value. This Poisson distribution won't work out there. So what we have to do is we need to add up all these values, okay, and all these values plus 7 or more will be equal to 180. So we just need to subtract 180 with all these values. So it's 14.775 minus 36.938 minus 46.173 minus 38.477 minus 24.048 minus 12.024, finally minus 5.0101 is equal to 2.5549. So it's 2.55. Have here 2.555. Okay, 2.5549. Let's keep it to 4 significant figures as we did all throughout. 5 significant. So 2.5549. So these are all our values. Okay, next, moving on, we need to do the summation formula. So that is going to be sum of our test statistic, okay, is equal to our observed value minus our expected value whole divided by, oh wait, multiplied, whole square this and then divide by expected value. So this is the formula that's used in almost every single test, and this formula only applies when our expected value or expected frequency is greater than 5. In this case, our last value is not greater than 5. So what we must do here is we need to combine this value and the value right before it, which is 5.0101. So we're going to combine these two. So 5.0101, which is equal to, no wait, not multiply. So let's just get back our value there. And then we add this with 5.0101 is equal to 7.565. So I'm just going to erase this, okay, and I'm going to put here 7 point, okay, I'm going to just put that back in black, so 7.565. okay, notice that we need to combine our total frequencies as well. Okay, we need to combine the frequency that we've had over here, so we need to combine these two. Okay, so when we get, this is when 6 or more, this is when you get 6 or more, this is 5 4 3 2 1 0. So let's just put this here, 0 1 2 3 4 5. okay, we have this right here, 6 or more, that's the probability, that's the expected value. We have to combine these two, so when we combine these two, our observed frequency still doesn't change, it's going to be 10. So now we have to use the formula. We are finally able to use the formula because every expected value is greater than 5. So using the formula above, you can state observed value of 21 minus the expected value of 14.775 whole square the difference whole divided by expected value, which is 14.775. okay, so we're going to add this on with, okay, let's actually get the actual value for this one, so 2.6227, or let's, even better is just to go by fractions because that gives a more accurate value. So over here 21 minus 14.775 whole square that difference whole divided with our expected value, which is 14.775, and this is added on with, observed value 33 minus this with expected value 36.938. So I'm going to just bracket this and then a whole square by number of turns, which is 36.938. okay, and this has to be repeated for every single value. So let's move on here. Observed value for when r equals 2 is 46. Subtract that with our expected value, which is 46.173 whole square the difference whole divided with 46.173. This is going to be a very small value because there's a very small difference between the observed and expected. So we have, next up, r equals 3. When r equals 3, our observed value is 31 minus this with our expected value 38.477 whole square the difference whole divided with 38.477. close bracket. Now when r equals to 4, when r equals 4, observed becomes 23, but our expected frequency was 24.048. Whole square that difference and divide it with our expected value again, so it's 24.048. That's our expected value right there. So that's when r equals to 4. Now when r equals 5, observed becomes 16. So let's just add this on with 16 minus expected, which is 12.024, 024 whole square, divide this with 12.204, then add this on with 6 when r equals to 6 or more, so it's going to be 7.565. Combining these two frequencies gives us 10, so it doesn't matter. So we have here 10 minus 7.565 whole square that difference, whole divided with 7.565. Okay, so that's all our values, and we will get, now we need to plug in each and every single value of this. So it's going to be tedious, but we have to ensure that each and every value is accurate, otherwise we could falter our value. So 33 minus 36.938, that is the frequency, whole square the difference, divided with 36.938, add this on with 46 minus 46.173, whole square that, and we have to divide this with the same expected, so 46.173, add this on with 31 minus 38.477, and we find the difference between the two, whole square it, and go back to 38.477. Moving on, we have 23 minus 24.048, whole square that difference, divided with 24.048, plus, now we have here 16 minus 12.024, whole square that, divided with 12.204, plus 10 minus 7.565, whole square that, divided with 7.565. Okay, looks like our value is too big to fit in the calculator, so I'm just going to reduce our last term. We get here gets this, and then we add this with our final term, 10 minus, okay wait, this also needs to be in bracket, so 10 minus 7.565 whole square that, divided with 7.565, which is equal to 6.62. Okay, now this is what we have for the test statistic. Now to find the critical values, you have to ensure that our degrees of freedom is correct for this. So how do we ensure the degrees of freedom is right when we have estimated so many parameters? So we have here, when we've calculated this test statistic, we've used 1, 2, 3, 4, 5, 6, 7 values. But given that this is 6 or more, we're going to be considering the number of terms as 6. Okay, this is 6 or more, so we don't consider this as just one. We have estimated a parameter, we've combined a column, so we just don't consider that, and therefore our degrees of freedom will be 1, 2, 3, 4, 5, 6 minus 1, which is our estimated parameter. So degree of freedom equals to 6 minus 1, which is equal to 5. And when we go to the chi-square distribution test over here, we need to find the p-value as well. P is going to be 1 minus alpha for chi-square test. It doesn't matter if it's single tail or two tailed, it's just 1 minus alpha all the time. So 10% significance level, meaning it's 0.9. So 0.1, 1 minus 0.1 equals to 0.9. Okay, so when you go to degree of freedom 5, we get critical value 9.236. Okay, now how do we represent this? How we refer is going to be chi squared. Now we write a degree of freedom here, 5. We write it in brackets the p-value, which is 0.90. Just put it as 0 because it's always referred to like that. And we have here 9.236. That's 9.236. Now we compare the two values, 9.236, our critical value, with our test statistic 6.62. Critical value is greater than test, so we accept H null. Accept H null. H null. Okay, that means that there is insufficient evidence to suggest that Poisson wait, let's just say it support the manager's claim. The manager's claim. I think it's a manager's claim, right? Yeah, the manager now takes and claims the number of this one. So it's insufficient evidence to support the manager's claim. Moving on. Yeah, CRV. Okay, continuous random variables. So they're asking us to find the CDF, which is cumulative distribution function, when we have PGF, which is this right here, and CDF is represented with capital F, just to let you know. And how do we do this? So for the first function, we just need to integrate 1 by 8, which just gives us 1 by 8x. Okay, we always integrate with respect to x. Okay, so that's our CDF for the first function. To find the CDF for the second function, it's going to be capital F, and then we put in the upper limit of the first function, which is capital F times 1 plus, now we have to integrate this 1 by 28. We can factorize the constant out of this, 8 minus, with limits x. Our upper limit is replaced with x, okay, and our lower limit will be 1 itself. 8 minus, and given that our upper limit is x, we can't have 8 minus x, so it will be 8 minus t, a dummy variable where x equals t, and we differentiate with respect to t, which gives us f1, capital F1, meaning CDF when x equals to 1. When x equals 1, even though in the inequality says x must be lower than 1 for this function, we are going to put x equals 1, which gives us 1 by 8 plus 1 by 28, and right here we have okay, when we do this we get 8t minus t squared by 2 with limits x and 1. Now we need to, this is where it gets the simplification part. No, we don't multiply yet. Okay, so 1 by 8 plus 1 by 28, multiply this with, now we put in the x value, which is 8x minus x squared by 2 whole divided by 2 minus, now we put in the lower limit 1, which is just minus 8. Notice that we have to put this in brackets, and then minus this with 1 squared by 2, which is just 1 by 2, which is equal to 1 by 8 plus 1 by 28. Now we factorize this, and we have here 8x minus this x squared by 2, which can't really be simplified just yet. and minus 8 minus 8 minus 1 by 2. 8 minus 1 by 2 is going to be 15 by 2 or 7.5, and when we have a negative over here we have negative 7.5 or 15 by 2, any would be fine, but given that we've written fraction here, I think it's more appropriate if we write 15 by 2. Okay, moving on. You can see that there's a denominator of 2 for most of our values inside the bracket. So let's multiply 2 inside the bracket and increase our denominator with 1 by 2. So 1 by 8 plus 1 by 56. Okay, and here we're going to have 16x minus x squared. Okay, 16x minus x squared, or actually let's keep this into simple terms. Instead of multiplying everything with this, let's take it outside the bracket itself. Okay, to just simplify this more easier, let's take this negative 15 by 2 out and then add this with 1 by 8. So when we do that, we get 1 by 28, and then we multiply this with negative 15 by 2, and then we add that with 1 by 8, which gives us negative 1 by 7. Okay. So with that being said, we've got 1 by 28, 8x minus x squared by 2, bracket minus 1 by 7. So we can simplify that, but we'll do that just later. So finally our CDF f of x is equal to, now we're going to write here, first thing that we do for a CDF is put 0 on the top and 1 all the way below. Okay, this is just a format that you have to follow, and this is when x is going to be lower than the lower limit of the first function, which means x is lower than 0. This happens when 1 happens when x is greater than the upper limit of the function, which means x is greater than 8. Okay, now we state the CDF for the first one, which is 1 by 8x or 8 or x by 8, and this happens between the range 0 to 1. And our second value is going to be 1 by 28 or 1 by 56 if you want. 1 by 56, we've just multiplied everything inside. 16x minus x squared minus 1 by 7. That's 1 by 7. Okay, and this is going to happen in the range between 1 to 8. So that's a CDF. Now to find the value of a constant a such that the probability of x is lower than or equal to a is 5 by 7. Okay, so first of all, the probability is 5 by 7. That means that our first function of CDF, 1 by 8x, when you plug in 1, you get 1 by 8. That is clearly lower than 5 by 7. That means that this probability will lie in the second function, which means, in other words, 1 by 56 16x minus x squared minus 1 by 7 is going to be equal to your 5 by 7, right? Okay, so we got that set. Now we can simplify this. So we have 1 by 56 16x minus x squared, and when you add 1 by 7 5 by 7, you get 6 by 7. Okay, and let's multiply both sides with 56. So we have 16x minus x squared is equal to 56 times 5 by 6. So 56 itself is going to be a multiple of 7, which is with 8. So we're doing 8 times 6, or in other words, it's just going to be 48. Yeah, 48. Okay, that means that you get this right here, but you have to also notice that this is when the CDF, when a is equal to x. Okay, we have to consider a equals x, so that is something that you have to consider for that. So we can just replace every value of x before with a. It's much faster, much easier if you do this. a a Let's just cut off every single value of x with a. Or we can consider write x equals a and then write this equation, but I think the Cambridge would prefer putting a in the first place. So a minus a squared and then 16a here, a squared here. Okay, now to solve for this, I'm not going to be solving it directly like that because that is going to consume a lot of time. So I'm going to go menu and then going to go to this right here. It's going to show equation slash function, but this is in German, where this is simultaneous equation or polynomials. We want polynomials of degree 2. So 1 is the coefficient of a squared, negative 16, and finally 48. So x equals or a equals to 12 or a is equal to 4. Now I can tell that a equals 4. You know why? Because a must lie between 0 and 8. It's going to be lying between 1 and 8 actually, because it doesn't apply to the first function. That means a equals to 4. That is your answer. It must stay in the range. 12 is beyond that range. And finally we have to substitute and find the PDF of y. Simple. So we're going to consider this as y equals to, we're going to just put it in smaller letters now, and that means when we cube both sides, x is equal to y cube. Okay, now the reason that they've given this in capital is because we can't plug this in when we have a small x. Okay, this we can't plug this in directly over here. We need to plug it into a CDF first. So our CDF becomes, well, firstly we have to put gy is equal to, now we need to specify the ranges. Okay, so when it is 0, this applies from, for x it applies from x lower than 0. So that means y cube must be lower than 0. That means that y is still going to be lesser than 0. So this is going to be when y is less than 0. Moving on, 1 by 8x. So that means 1 by 8 y cube. Okay, and this applies when x is between 0 and 1. That means y cube must lie between 0 and 1. Okay, so we've already simplified this and we got 0 greater than equal to y, 0 less than equal to y. However, y cube by 1, we need to find the cube root of 1. That is going to just be 1 itself. It's just going to be 1. So that means we found our range for when y cube is substituted to x. So we have here 0, y, 1. Now we have to substitute the next value now into our big function right here, 1 by 56 x minus x squared and all that. Plug in x equals y cube. So you get here, I'm going to keep this 2 lines so that's more visible. 1 by 56 with 16 y cube minus x squared, and x squared is just y cube whole squared, and using the law of exponents, a times m whole to power n is equal to, that's n. Okay, a equals to power of mn. Similarly, y cube when whole squared is equal to y to power 6. Simple law of indices, so y to power 6. Okay, and this is subtracted with 1 by 7, our original CDF. And when does this apply? When for x it's going to be between 1 and 8. So for y, as we simplified here, it's going to be between 1 and, okay, so y cube must be lesser than or equal to 8. So when we cube root both sides, that means that y is going to be lesser than or equal to 2. So that's our range. Okay, we can erase this as well. We don't need this. It's already stated as follows. Moving on, and finally 1 must be, well, now we can just put y greater than 2. Okay, So that's our CDF for y. Now to find the PGF, very simple, we just put gy smaller case, okay, and we put here, okay, so in the last we're going to have 0 otherwise, but before that let's integrate. So when we integrate 1 by 8 y cube, we're going to get 3 by 8 y squared, okay, and this, the range stays the same, that will never change. So between, when you're converting between PGS and PDFs, the range never ever changes, so need not worry about that. Next we need to integrate this right here. So 1 by 7 just gets kicked out because it's a constant. We can still factorize 1 by 56, and over here it's going to be 16 times 3, which is just 48 y squared minus 5, no, minus 6 y to power 5. Okay, so if you want, you can factorize this further, although yeah, you can factorize this further, but it's not really necessary, so you can just leave it like this, so 0 otherwise. If you want, we can factorize the function there. We can factorize this because we can factorize 6 out of this and get 6 by 56 or 3 by 28 bracket 8y squared minus y to power 5. It isn't necessary, but it's quite optional really. And okay, you know what, let's do it for this. So we can factorize 6 out of this and we get 6y squared, no, 8y squared, 8y squared, y squared, and when we factorize 6 out, we just get y to power 5. And when we factorize 6, we can put 6 by 56. 6 by 56, well, it's just the same as 3 by 28. Just divide both the numerator and denominator with 2. So, and I'm just going to rewrite this entire function then. So 3 by 28 of 8y squared minus y to power 5. That right there is the answer for this question, and that concludes the paper 4.3 of the May-June series of 2021. I hope you enjoyed this video. Please ensure to like, share and subscribe, and I will see you in the next video. This has been Further Statistics. Goodbye.